Hi everyone, my name is Rishabh Mehrotra and I'm joining from London. I work at ShareChat, and today we're going to talk about algorithmic balancing models for multi-stakeholder recommendations. So just a quick introduction. So I recently joined ShareChat and I'm leading the feed and marketplace efforts here. Up until like January earlier this year, I was at Spotify doing a bunch of multi-objective marketplace machine learning. Before that, I had a PhD in machine learning from UCL in London. And in generally, I'm interested mostly in creator ecosystem and multi-objective machine learning and user modeling and personalization. So today we're going to talk about marketplace and stakeholders. So I'm going to motivate the problem by introducing some examples of different companies and really kind of bridge the gap between traditional recommender systems and modern recommender systems, which are multi-stakeholder platforms. With that background, I'm going to try to talk about what kind of algorithmic balancing machine learning we need to do. And to do that, I'm going to touch upon two main technologies we have developed over the last couple of years. One is on multi-objective contextual bandits, and the other one is on fuzzy aggregations. And towards the end, I'm going to end the talk by just giving some high-level overview on how do we leverage user, supplier, and content understanding to develop a good recommendation system. So let's start with some background. So traditionally, what has happened is recommender systems has been mostly user-centric. So people have kind of developed these systems for the last 20 years, and they mostly focus on user engagement, user experience. We've looked at user evaluation metrics, we've tracked user interaction profiles, we've developed these user personalization models, and users have been the core of the entire system design perspective for these traditional recommender systems. But again, like the question we want to ask today is caring about the user enough? And now if you start looking at a bunch of these upcoming companies like Netflix, Airbnb, Uber, ShareChat, even Spotify, Etsy, all of these are multi-stakeholder platforms. So what I mean by multi-stakeholder platform is that just optimizing and caring about user may not be enough. So here we have to look at maybe the delivery partners on Deliveroo or the drivers on Uber, and even like the platform economics comes into play as well. So again, how do we balance multiple objectives coming in from multiple stakeholders in terms of deciding the recommendations we surface in front of the users? So again, let me give you a couple of quick case studies. If you look at Uber Eats, then it's a three-sided marketplace looking at eaters, restaurant partners, and delivery partners. And again, if I start looking at the relevant objectives, then exposure of restaurants becomes an important objective. Earnings per delivery partner is an important objective. If I start looking at Airbnb, then it's a typical two-sided marketplace, which has guest and host. And again, like if you start looking at some of the potential objectives, like number of bookings per host, especially for the tail host, could also be one of the objective. Or how do we help hosts who host less often? So again, it's not just about making sure users get what they want, but also making sure that the platform is delivering enough exposure to some of these hosts as well. Same at Spotify. So Spotify cares about matching creator and user needs. So how do we enable creators to grow their audiences, and how do we give listeners some diverse listening experiences on the platform? And as I mentioned, like on ShareChat, which is one of the #1 social media company back in India, and here also we care about how do we balance the user and the creators. So we have close to 200 million MAUs now, a very vibrant creator ecosystem at play, like close to 100 million plus creators in total. And how do we start balancing the user goals with the creator goals and grow the entire marketplace in totality? So the key point over here is that once you start looking at some of these multi-stakeholder platforms, then you realize that we need to go from a recommendation strategy, which is just user-centric, and mature towards a multi-objective world. So here, instead of optimizing for just one function, we would rather look at how do we principally optimize for multiple objectives. So some are user-centric objectives, some are supply-centric objectives, some are platform economics, and so on. And in general, it's not just about multi-objective balancing from stakeholders. There's a lot of need for balancing in many, many different places. So again, you could look at balancing various user needs like familiarity, discovery, relevance. You can balance different user personalization with content hypotheses. You can balance the different content distribution on the platform. Like typical example could be a company like Netflix. They might care about originals versus source content, category 1 versus category 2, and so on. We also can balance short-term and long-term goals, balancing the creator goals itself. So some creators might want more engagement, some might want new fans, some might want monetization. So different creators are at different stages of their needs and demands. So again, like balancing those creator goals and then combining it all together. How do we balance user goal with creator goal, with content goal, with the platform revenue goals? So there's a lot of need for balancing. And this kind of brings us back to this core problem, that how do we balance multiple stakeholder objectives when we are designing these recommendation systems at scale? So what I'm going to do next is, in the next 20 minutes or so, I'm going to dive into a couple of these core technologies, which you can think about when you start to design some of these systems. So what we're going to do is, like, we're going to focus on balancing multiple goals. So let me give you just a quick example of what type of balancing we are talking about. So again, if you look at a bunch of objectives, like let's look at three objectives from user satisfaction, one supply diversity, and another promotion objective on the platform. We start, and the heat map over here on the right is the correlation between these objectives. So you start seeing that different satisfaction metrics are correlated with each other, and that's good, because if you optimize for one, you're going to get the others for free. But then you start seeing that some of the supply diversity metrics are almost neutral with satisfaction. So that means, like, if you really have to improve some of these metrics, you cannot get it for free. You'll have to optimize for it. But increasingly, more and more of these objectives start becoming anti-correlated with satisfaction or some other objective. So then you start dealing with this trade-off that I can either win some or lose some. So the question then becomes, like, if this interplay exists between these objectives, then how can a machine learning model kind of balance and trade off across these objectives? So again, that's the key question which we want to answer. And we're going to talk about two types of approaches. One is a bandit-based approach, and the other one is, what if you don't have a bandit-based approach? So again, if you look at the industry, a lot of these machine learning systems powering some recommender systems have matured into a contextual bandit-based solution. So for that, we're going to talk about one set of algorithms. And for the others, and a lot more generic case, we're going to talk about what if you have a neural network powering your recommender systems, and what kind of multi-objective decisioning you can do there. So let's start with the bandit-based recommender. And once we've gone through it, we'll come back to the more general case of aggregation functions. So this is some work which we presented at KDD a couple of years ago. And essentially, like this, we bring back the same problem, that what kind of multi-objective functions can we optimize in a bandit setting? So the long story short is that what we did was we leveraged this generalized Gini function. And we said that, hey, in a contextual bandit setting, let me optimize for this function, which is a special form of ordered weighted average. So it preserves impartiality with respect to the individual criteria. So I'm going to talk about why this function, what are some good mathematical characteristics of this function. But one key takeaway, which I'm going to come back to in the next few slides, is that this function prefers allocations that are more equitable. So now, if you have a multi-objective world, right? I mean, if you have a multi-objective problem, in a bandit setting, you'll have multiple reward functions, and then you want to balance and have a more equitable allocations across your reward functions. So again, this is what this function allows us to achieve. So let me kind of go into detail of what this function does and why it's kind of, it has some nice mathematical properties for us. So again, GGF is a special form of ordered weighted average. So what exactly does an ordered weighted average mean? So what exactly it means is that we are assigning a weight not to the attributes, but to the sorted scores. So imagine you have an item I, and for each item X, you can have, let's say, 4 or 5 objectives. So now, instead of saying that, hey, each time I'm going to assign a weight of W1 to my attribute X1, you say that, okay, I'm not going to assign the weights to attributes, but instead to the sorted scores. So what I do is, like, we look at the sorting of the scores based on all the objectives. So each item has, let's say, 5 objectives. So you have these 5 scores. You can sort based on that score, and then you're going to assign W1 weight to the highest score you have. So what's the deal here? Why do we do that? We do that because it allows us to dynamically control importance given to attributes. So in a typical weighted sum, you're going to assign your weights to one attribute, and that's going to be fixed. But instead here, we do that, hey, I'm not assigning a weight to any specific attribute. I'm going to assign weight to the maximum scoring of these attributes. So that allows us dynamic control. And one of the good things is that this kind of function respects this pigeon delta transfer. It kind of prefers allocations that are more equitable. And let me show you how. So basically, the pigeon delta transfer says that if you're doing a gap diminishing transfer from someone with more to someone with less, it's going to decrease inequality. So it's a very intuitive way. It says that, hey, if you have, let's say you have like 3 objectives. For each of these 3 objectives, you have 3 rewards. And right now, you're really doing well on the third, but you're not so doing well on the second and first. But if you take something away from third and give it to the second, then what you're doing is you're taking something from someone which has more and giving it to someone which has less, and it's going to decrease the inequality. And this is what a GGA function allows you to do. So this is what the pigeon delta principle also kind of facilitates. So it's kind of a kinder, gentler cousin of the Pareto optimality. So Pareto optimality prefers efficiency, right? I mean, it's saying that I want to be Pareto efficient, but the pigeon delta transfer prefers equity across the different dimensions you care about. So again, in a multi-objective world, you can say that I care about 5 objectives, so these are my 5 dimensions, and I want to be equitable across each of my objectives. So again, like as I mentioned, that the GGF respects this equitable allocation, and what that means for us is that let's say we have a reward vector x, and xj is greater than xi. So now what we do is, like, if I take something away from xj and give it to xi, so then this is a diminishing, it's a reward balancing mechanism. And this resulting x is going to have a higher Gini function than the previous x. So again, this is what kind of this principle entails, that you're transferring from someone with more to someone with less. So again, this allows us to balance the reward vector, and we can use it as a measure of balancedness. Now, what happens is that we can solve for this GGF using some linear programs, and but again, that's not scalable, it's not computationally efficient. So then we propose a gradient SN-based solution here. So I'm going to kind of sidetrack a bunch of contextual bandit formulation here, but essentially what we end up doing is we have a typical contextual bandit setting wherein the goal is to find the arm selection strategy. For each round, we get a bunch of contextual features. We have the reward formulation, and the reward is not a scalar reward because it's a multi-objective function. So then we have multiple reward functions. So it's a vectorial reward. Now, the core of this is that when you're trying to train your contextual bandit model, you can go back and leverage the GGA function and train your bandit model around this GGA function. So now, because this GGA function prefers equitable allocation, so now you're doing a lot better multi-objective modeling inside your contextual bandit model. So let's take a step back. What we've done, we've said that traditionally, contextual bandit models are trained as single objective functions. So now what we said is that, no, I mean, there is a class of functions which prefer more equitable allocation across its components. So then let's use that function. So we have wrapped up the contextual bandit model around this GGA function, and this allows us to balance the reward. And each reward translates to one of these objectives. So you're now having more balancing across the different reward functions. So again, we tried to apply this at Spotify, and in general, we saw that even if you just optimize for user satisfaction, then a multi-objective satisfaction model performs better for each metric than directly optimizing for that metric. So again, even if you don't care about marketplace and multi-objectiveness, if you just care about satisfaction, then optimizing for multiple satisfaction is better. And the moment we start adding some competing objectives, we start seeing some gains. And this is a great example to show that it need not be a zero-sum game. So maybe you can get some gains in your non-user objectives without hurting your user satisfaction metrics. So again, this was a typical case for what we could do when we have a bandit setting. So if you have a bandit model, you can swap in and swap out with a GGF function, and that will give you a multi-objective system. But what if you don't have a bandit-based solution? What if you don't care about explore, exploit, and exploration in your recommended systems? So here we're going to talk about general fuzzy aggregation techniques. So if I have a bunch of functions, bunch of scores, then how do I kind of combine it and scalarize it even outside of a contextual bandit setting? So this is a research which we published last year at CIKM. And this paper talks about a bunch of the A/B tests and the deployment which we did across 400 million users at scale. So essentially, like, what the background is that you have a user and you have a bunch of items. And for each item, you can have your favorite neural network, or logistic regression, or even cosine similarities. And for each item, you can get a score for each user. That what's the probability of user consuming the score? So it could be a relevance score. It could be a probability of user streaming it or user liking it. But in a multi-objective world, you add a multi-objective decorator. So you're saying that, hey, it's not just about the user relevance score, but I do care about discovery, exposure, boosting. I care about 3 other objectives. So each item now gets tagged with these 4 scores. And then you want to kind of do this multi-objective balancing. And this is where the balancer lies. So the balancer is saying that, tell me the different composition scores, and I'm going to aggregate them into a one single score. So this is your multi-objective function, which we are after. So essentially, a typical way to do that is, let's say you have relevant score, you have creator objective, you have discovery, and then you're going to combine these scores. So you can combine them using just a weighted sum, or you could do something else. So essentially, what we want to do is we want to design some aggregation functions which have some very special properties. So some of these properties are, as system designers, I might want to have function which gives me this property that, hey, give me a high score if any of these objectives are good. So if your track or your item satisfies at least one criteria, this is good enough for me. So then give me a high score. So that example would be that if, let's say, you only care about satisfaction, then any of the following are good. So if the user is streaming the track, or user is hearting a track, or user is saving the track for later, as long as any of this is good, it's good enough for me. So in this case, I want to have a or style functionality in my function. On the other hand, sometimes as a system designer, I want not or, but and. So it's like, no. Give me all of these attributes, and then only it's a good enough item for me. So here, right, I mean, we can say that select me tracks and items which are great for the user, but also great for the creator. And then only I'll kind of consider it a good item. So again, oftentimes you go between the two. Either you have an or function that if any of these is good enough, I think it's a good enough item. Or no, I want all of these criteria to be met, then only I'll consider it a good item. So we need this property. And as I mentioned before, we need to be able to dynamically adjust the importance based on scores. So traditional weighted sums, right? I mean, they assign the weights to a specific objective. So there's a static weight assigned, the weight assignment, the weights can change, but the weight assignment is fixed to the attributes. Here, what we're saying is that if you rely on the OWA functions like ordered weighted averages, then you're not assigning weight to predetermined objectives. You're looking at the scores dynamically in real time and then assigning weights accordingly. So this kind of motivates the need for richer aggregation functions, and weighted sums and typical functions don't give me this property. So this is where like we propose this OWA balancing. So again, as I mentioned before, OWA is an aggregation function that associates weight not with an objective, but with their magnitude. So essentially what we do is like, give me an item. For each item, let's say I have n objectives. So I'll have n scores for each of these objectives, of each of these objectives, yeah. So for each item, I might have the relevance score, I might have the creator success score, I might have the revenue score, I might have some other objective as well. What I do then is I sort them based on a decreasing order. So once I have that, then I use a weight quantify function. And this weight quantify function gives me the weight for each of these attributes. So because I have done a sorting, so the first, the score at the first position is the maximum score. So now I want to assign a weight to that one. And this function, which I'm presenting over here, we call it the rim quantifier is regular increasing monotone quantifier. And they allow us to express this fuzzy majority objective. Like, as I was mentioning before, that I want this property that as at least some of these criteria are met, or as many of these criteria are met. So let me show you how exactly it happens. So the function which I showed here, right? I mean, this weight assignment function, it has this property. So if you have alpha, right? I mean, if you have the alpha parameter less than 1, then it assigns a very high W1, and W2 and W3 are pretty low. So because W1 is assigned to the highest score among the 5 objectives you had, so then the first attribute, because it's sorting, right? You've done that sorting at the start. So the first attribute score is always a max, and W1 is high enough. So the moment W1 is high, then and because the A1 attribute was the highest scoring because you had done that sort by decreasing order, W1 A1 becomes high. So the moment W1 A1 becomes high, the importance given to attribute 2 and 3, it kind of decreases. Why? Because W2 and W3 are small enough. So this is how we get the OR property. Now here's what's happening. Let's say you have five attribute scores, and because you've done that sorting at step 1, then the first attribute is always the highest. And if you're assigning a high weight to the first attribute, then the moment any of these attributes becomes high, it goes to rank 1, and W1 is assigned to rank 1. So that means W1 rank 1 is high enough. So then all the others are not as important. So this gives you this OR property. Why? Because the moment any of this become high, then the overall score becomes high. On the other hand, if you have a different setting of this alpha parameter, you can say that, hey, if alpha is greater than 1, then the W1 is low, W2 is low, and W3 is low as well. So here, right, I mean, in order to get an overall high score, you want to have all of these attributes to be high. Why? Because there is no one attribute which is getting an high enough weight. So the overall item will get a high score only if all of the attributes are high enough. So just juggling between these parameters gives you a sliding window between and or. Let me explain how we use it. So once you have these weights, you can combine them using traditional weighted sums. So let me give you an example of how it actually does this and or property. So if I care about at least one criteria, then let's say I have 3 objectives and I have 3 items. So for the first item, I have 0.1, 0.2, 0.3, and for track 2 and track 3, I have different scores. If you look at the OW output, then if all of these were low, then I get a low score. But the moment one of them becomes high, I get an overall high score. And if all of these are high, I still get a high score. But the jump in magnitude is pretty significant the moment one becomes high. So alpha less than 1 gives me this OR property. On the other hand, if I do alpha greater than 1, then let's see what happens. So in the case when only one of these scores become high, the overall net score for the item didn't increase much. It went from 0.100 to 102. But the moment all of these attribute scores become high, then only we start getting high scores. So this is what exactly we wanted. We wanted to control this and or property, and now we have a mathematical function which gives us that. So again, like one of the core benefits of this is that once I have this function, I can stack them together. And it's, I mean, like Lego blocks. So essentially, let's say I'm a system designer and I care about satisfaction. So if any of my satisfaction goals are achieved, it is good enough for me. So I'll do an OWA of alpha less than 1, and I'll get this. Same for creators. I have a bunch of creator objectives, and I'm going to do an OWA of creator with alpha less than 1, and I'll get that. But now I want to make sure that my recommendations are good for both the creator and the users. So then I can do another OWA, but with alpha greater than 1. So you can design, using Lego block style thinking, you can design your multi-objective formulation system in a very easy way. And you can just tweak your parameters alpha to support whatever multi-objective balancing you want to do. And again, like we performed a bunch of large-scale experiments and deployed some of this at scale on the radio platform at Spotify. And we saw some pretty amazing wins. We saw that some of these hierarchical OWA functions are giving you gains in a lot of like competing objectives. So again, it's helping users, it's increasing the return rate, it's increasing discoveries, increasing the artist metrics. So again, we got a lot of like great metric wins. And again, one of the core benefits of this is that it's very easy to implement and easy to design. The hyperparameter tuning is something which you'll have to pay attention to. But outside of that, it's a pretty easy system to work with. And again, we also saw some impact on suppliers. Like, I mean, we were able to shift consumption towards more tail suppliers, which was one of the intention goals here. So essentially, like, I mean, what the quick takeaway so far has been that, look, there's a need for multi-objective modeling, and you can either do it in a banded setting. There we propose a GGF-based function, which prefers equitable allocation, or you can come back and look at aggregations. And here we proposed a fuzzy aggregation-based function. And this allows you to kind of encode a lot of these system design heuristics very easily in a nice mathematical formulation. Let me quickly end in the last couple of minutes by just talking about that it's not just a core multi-objective machine learning model, which you should pay attention to, but you should develop a lot of satellite components which will help the core ML model make a better decision. So I'll give you a quick 3 to 4 examples of what some of these look like for us. So again, like, how do we make the balancing decision better by looking at user metrics, user insights, by looking at supplier insights, by looking at content insights? So we had a paper at Rexis wherein we were talking about user receptivity. So can I predict user tolerance and user receptivity to some of these objectives? So if I can make that prediction, then I can use that user receptivity to better target users. So like, some users might like discovery, some users might not like discovery. Some users might be okay with non-popular creators, some users are not okay with it. So if you're able to predict that user propensity, then you can use that to inform the balancing decision. Now your multi-objective model knows something more about the user, and then it can route the objectives accordingly. Another line of work we did was that diversity is important. Like, I mean, on your platform, if users are consuming diverse content, then you get a lot more power. I mean, you can use diversity to showcase some tail artists, tail creators, and even like bring up a few categories which are not so popular on your platform. So we did some work which was published at Wisdom last year, which is talking about how do we design these RL systems which have a reward function which optimize for and allow for diversity as well. In a multi-objective world, you want to kind of care about disentangling the effect, right? I mean, because you're making a multi-objective decision, then it's very hard sometimes to understand that if something went wrong, then who's the culprit, right? So how do you disentangle the causal effect from a set of multiple interventions? So again, a lot of like causal impact modeling work is needed to tease apart some of these impact, especially in a multi-objective setting. So we have a line of work which is starting to look into that. And finally, right, I mean, you want to control these trade-offs. So we kind of, at a paper we are presenting at the web conference later this year, we talk about how do you design a flexible system which allows you to control the trade-off. Because in industrial systems, you have OKRs, you have to hit some goals, and then you want to keep track of how much of a metric win are you already getting and how much is the urgency for some other objectives. So based on how you're performing, you can have these adaptive feedback loops and then use that to decide the real-time trade-off. So again, that's what we propose in the paper, which is coming up in April at the web conference this year. And just one last bit, and I'll kind of end by just making this last point, that in a multi-objective world, it's very important to decide how do you make rollout decisions, because each change will impact a bunch of different stakeholders. So what trade-offs are allowed, what trade-offs are preferred. There's a lot of work which needs to happen in the measurement world. That if I gain something on objective 1, is that good enough for objective 2? What kind of trade-offs are okay? What kind of trade-offs are not okay? What's the exchange rate between some of your objectives? All of these are very nice and very non-trivial measurement problems for us to tackle. With that, I will end this presentation and just present this last picture that if you start looking at some of these recommendation systems powering multi-stakeholder platforms, then like you got to do this balancing, you got to understand users, suppliers, and the platform, have measurement, have adaptive decisioning, feedback, and then do holistic evaluation. So it's more of an ecosystem design rather than one specific algorithm design, which we are after. So with this, thank you so much for attending. I'm happy to take questions now.
Welcome, Rishabh.
Thank you. Hi, good to be here.
Thank you for your presentation. It was really interesting. The first question is, what are the difficulties in evaluating such recommender systems?
Yeah, I'm glad this question got asked because I think like I really like the modeling of these systems, but evaluating them is a nightmare. Because imagine, right? I mean, it's not just evaluating, but also controlling these systems in real life, right? So as a platform owner, you got to have multiple objectives, multiple stakeholders, and there's a bunch of very interesting trade-off which exists between these metrics. So as I mentioned, just briefly towards the end, that how do we make shift decisions? So now you've done a bunch of A/B tests, you have 3 or 4 candidate policies which you want to roll out to maybe 100% of your production traffic. But then like each of these come with a different set of trade-off. Now, one model might give you a 5% gain in objective 1, but only a 3.5% gain in objective 2. The other model might give you a 4% gain in objective 1, but a 3% gain in objective 2. So how do you compare a bunch of policies on multiple dimensions? So this is where like things like platform governance comes in. So we've done a couple of initiatives in that direction. One is that we've laid out an order of priority across these objectives. And then we also have a bunch of guardrail metrics. So guardrail metrics allow us to make sure that while we are optimizing for some of these metrics, we are not harming one of those guardrail metrics. The other science project, which is involved in evaluating such multi-objective problems, is how do you develop the exchange rate between your objectives? So like, I mean, if you look at currencies, right? I mean, every currency doesn't exchange in themselves. I mean, they kind of, US dollar is one of those currencies which everybody kind of uses as the single currency, and then US dollar is pegged to gold. But essentially, what do you do here? I mean, like maybe you have to do some exchange rate across your objective. That is a 2% of objective 1. Is it equivalent to a 3.5% of objective 2 or a 4% of objective 3? So how do we understand this? We develop some of these exchange rate models, and oftentimes, right, things like LTV come into play. That if you have a way to quantify the long-term value of the content or of the user, then maybe you can translate all of these metrics to LTV, and that LTV could be the common denominator currency based on which you can deal around these trade-offs. So it's a bunch of very interesting problems. And again, I don't think the evaluation and search recommender community has solved these problems, but now we are starting to develop some early frameworks to evaluate the trade-off across some of these decisions.
Mm-hmm. The next question says, Rishabh, first of all, thanks for a great talk. How does your approach work in terms of A/B tests? For example, how can we determine statistical significance? Yeah, so
Yeah.
this.
Yeah, thanks for the comment. I'm glad you like the talk. Essentially, like I mean, there's two questions, right? I mean, one is that how do we evaluate, how does it perform in an A/B test? So if you look at some of the recent paper, like the second paper we had last year on algorithmic balancing, there we provide a series of like results from close to 6 to 7 A/B tests, which is eventually deployed on Spotify. So again, if you're using the radio feature or any of your playlists, you are getting served your recommendations from a multi-objective model, which we developed as part of this problem. So again, like it performed very well because it was able to give us user satisfaction gains. It was able to give us discovery gain. It was able to give us gains on the creator objective and a couple of business objectives as well. So that's the benefit, right? I mean, if you model the problem in a nice multi-objective solution, then it can find these efficient solutions wherein all boats can rise at once. So again, like if you do it right, it's not a guarantee that you're going to increase all your objectives, all your metrics, but at least like once in a year, if you're lucky, you'll get some good modeling decisions which will improve all the metrics and everybody will go home happier and richer. But again, it's very hard to do that. Uh, at the same time, right? I mean, you mentioned about statistical significance. So again, I imagine like in a multi-stakeholder platform, you are bringing in non-user goals. So one of the things which we've done is we've tried to identify the worst hit users as well and make sure that in aggregate, maybe the system is better off, but maybe there is a segment of users who are not better off and who are kind of getting hurt disproportionately higher. So there we have some of these methods like difference in quantiles metrics. We have some things like poison bootstrap difference in quantiles, which we have started to use to understand not just the aggregate metric impact. So you're not doing just two-tailed test significance test on the aggregate, but also you're looking at the quantile-based performance and seeing that maybe in aggregate you are well off, but maybe in quantiles you're kind of disproportionately worse for a certain segment of users. So again, what's the point? The point is that look, often when you have a system wherein you have goals which are not just about user, you got to make sure that you're not just doing measurement at the aggregate level, but then look at what's happening across the segment of users, across the content categories, and then do a more holistic evaluation over there.
Mm-hmm. We have one last question, and we're
Sure.
running out of time. So, like, if you could briefly comment on that. During your research, have you also explored the subject of correlating online metrics with offline metrics? With so many objectives, is it feasible at all?
Yeah, I'm so glad like evaluation questions are coming up because people are really thinking about like this problem, right? So I mean, you're gonna ask an evaluation question only if you actually care about deploying the solution. So I'm glad the audience is focused on that. Uh, Offline online correlation is a nightmare hard problem for any industry to solve. So again, at Spotify, we spent close to like 1 year in 2019, 2020 to develop these counterfactual evaluation metrics. So for counterfactual evaluation, we collect some randomized data and then we develop these unbiased estimates. Now we did that for single objective methods and then we borrowed them for multi-objective. Now, if you look at the multi-objective metrics, some of these metrics are user metrics, and hopefully for user metrics, you already have a counterfactual unbiased estimator which you can use. Some of the other objectives are just factual objectives, like is this a discovery content for the user, or is this a tail artist or a tail creator? So again, for a bunch of non-user goals, these are just factual. So this is it is there or it is not there. So I think like you don't suffer from very bad offline online correlations for some of those metrics. You suffer from bad offline online correlation for the user satisfaction metrics. And for that, luckily, like the industry has, at least in the academic industry and like the research industry has a bunch of counterfactual evaluation techniques using randomized data and unbiased estimators, which we have used. And I think like last thing, and I'll stop, we are in the process of developing these sequential counterfactuals as well. So we have a paper at KDD just last year, which is looking at how do you do counterfactual evaluation in a sequential recommendation setting. So again, I really encourage you to go look at that because I think that touches upon a lot of very cool evaluation ideas there.
Mhm. Thank you for your answers. Is there something you'd like to add?
No, I think like overall, I just my pitch is that look, I mean, you guys are owning some of these design choices of your recommender systems. So I think like the overall point of the talk, and hopefully my message should be that let's be explicit about the objectives you care about your system and bring them to like make them first class citizens of your recommender models. Like give them a seat at the objective table, optimize for them, be very thorough in measuring and evaluating across those dimensions. And I think like you'll end up with a much better monitored system than before.
Mhm. Thank you very much. Thank you for the talk and your answers.
Thanks, Eva.